Now we're prepared to state all of these properties of common logarithms, and we have some general properties and the common logarithms properties. So the first is log base b of 1 is equal to 0. That's true for any base, so that's definitely true for common log. Log base 10 of 1 equals 0. We also have log base b of b equals 1, and the common log version of that is log base 10 of 10 equals 1. Log base b of b to the x is equal to x. That's our inverse property, along with b to the log base b of x, which equals x. And the common log version, we have log of 10 to the x equals x, and 10 to the log x equals x. Those same properties apply with a different base of natural logarithm, base e. I'm not going to read those again, but change each of those respectively to natural log of 1 equals 0, natural log of e equals 1, natural log of e to the x equals x, and e to the natural log of x equals x. And we can use those properties, again, for general bases of any base. Those properties apply specifically to natural and common logs. Now we can use those properties to discuss some characteristics of logarithmic functions. These are functions of the form f of x equals log base b of x. Now let me draw a couple of graphs to the right. The first is going to be an exponential function. So as we saw, it has a horizontal asymptote of y equals 0. And it grows as you're going to the right. It increases very rapidly. And it goes through the point 0, 1. Okay? That would be a function of the form b to the x. Now I'm going to draw a diagonal line. Okay, this is actually the line y equals x. This is based off the fact that these are inverses of each other. If I reflect this line, or this graph, exponential function, across that line, I get something, a function, that does not have a horizontal asymptote. It instead has a vertical asymptote. Okay? That is the logarithmic function. I have a vertical asymptote at x equals 0, the vertical line, x equals 0. It increases to the right when my base is greater than 1, and it actually between 0 and if the base is between 0 and 1, then it actually decreases to the right. So let's run through these properties. The domain of f of x equals log base b of x is all positive real numbers, 0 to infinity. Whereas with the exponential, we had a domain of all real numbers, minus infinity to infinity, and a range of 0 to infinity. With the logarithmic function, we have a domain of 0 to infinity and a range of all real numbers, minus infinity to infinity. The graphs of all logarithmic functions of the form f of x equals log base b of x pass through the point 1, 0. Okay, we're interchanging those points. Rather than the point 0, 1 on the exponential, we have 0, 1. And that is the x-intercept. It's based off our log properties. There is no y-intercept because it's a vertical asymptote there. Now, as we already said, if the base is greater than 1, if b is greater than 1, f of x equals log base b of x has a graph that goes up to the right and is an increasing function. If the base is between 0 and 1, we've said it can't be 0 and it can't be 1. If it's between 0 and 1, f of x equals log base b of x has a graph that goes down to the right and is a decreasing function. And then, as Art previously stated, the graph of f of x equals log base b of x approaches but does not touch the y-axis as compared to the exponential function. The y-axis, or x equals 0, is a vertical asymptote as opposed to the horizontal asymptote we discussed before.